So we've looked at root locus plots, Bode plots, and now we're talking about Nyquist plots. Here's an example of when a Bode is not actually very useful. So here's a transfer function, g of s equals k times s plus 10 quantity squared divided by s cubed. So let's do some analysis here. I'd like to plot Bode for some k. So for example, we can choose k equals to 7. And so this is some gain. I'm going to plot the Bode at this gain and see how the system seems to behave to indicate whether or not it happens to be stable. So here we have our Bode Axes, and this, for example, looks like the kind of plot that you'd expect for something like this. So we have minus 60 dB per decade until we get to about omega equals 0.1, and then things are going to change. Let me go ahead and put some graph paper on here so we can see how this looks. So we sort of slope down, and then we slope down maybe at a slightly worse angle after we get to omega equals 10. But if we look at the complementary phase, we start out at really sort of a terrible value, minus 270, and then as we add two more zeros, we're going to eventually work our way back up above 180, but it's going to take a while to do it. And so if we look at our gain margin here, which is where we pass minus 180, if we look at our gain margin, it's equal to minus 3, so that tells us that we're not stable. But our phase margin is positive, 10 degrees. So typically, and yeah, here, so just to categorize this, we have a gain margin that's negative and a phase margin greater than 0. But this is not what we'd like to see in a Bode plot. Usually, and of course this isn't very useful, so usually for stability of a Bode plot, our requirements are that the gain margin is greater than 1 and the phase margin is greater than 0. But strangely, because we have phase that's increasing after a certain point here, it turns out that we're actually not able to use Bode to tell about the stability of the system for this gain, because it looks from this gain like our system is unstable. But yeah, and of course, because we usually expect gain margin to be here when we cross 180 degrees. So we expect a positive gain margin for stability. But it turns out this system is totally stable at k equals 7. So we can see this by checking with root locus. So using root locus, we can verify that the system is stable. So here's our real and imaginary axes. And remember, our transfer function is s plus 10 squared over s cubed. So here we, of course, disregard k when we're producing the root locus because we're going to vary k from 0 all the way to infinity. So we have 3 poles here at s equals 0 and 2 zeros at s equals 10. Or sorry, s equals minus 10. So laying out the real axis points, this is where we see that the root locus is going to lie on the real axis because we have an odd number of poles or zeros to the right. So first here I'm going to check the breakaway points. So checking the breakaway points, we take the inverse of our transfer function and negate it, and then we take its derivative and set it equal to 0. A derivative with respect to s, and set that equal to 0 and solve for the s values. So dp ds equals 0 equals sort of, the standard division rule that you use for taking the derivative of a complicated function. So we do a lot more algebra, and then we end up with this equality. 3s squared times some quantity equals s cubed times some other quantity. So this is a fourth order polynomial. We're going to expect to have 4 zeros for the system. So we can right away see that 2 of them are at s equals 0. So for 2 values, s equals 0 and 0, we can find a 0 for this system. So now we'll take away 2 of those and multiply out and solve again. So now let's take the 2s squared plus 20s over to the other side and find the roots of this polynomial. It gives us s equals to minus 10, minus 30, and then of course the 2 zeros that we had before. So this gives us the locations of the breakaway points. It seems, usually when we've seen breakaway points in a root locus, it's been pretty easy to tell which ones they are because the breakaway points are actually the only parts on the real axis where we could possibly break away. But here we have a couple of different possibilities. So we could have a breakaway at minus 10, or at minus 30, or 0. All of those are actually on the root locus, and they're on the real axis. And so I don't know how our breakaway is going to behave, which motivates me. I'll just record these values here. So this motivates me to now look at the angles of arrival and the angles of departure. But in between, I'm going to check to see where we cross j omega. So of course, to do this, we're going to use Ruth Analysis. So we close the loop and set k times the numerator plus the denominator. And now we're going to do Ruth Analysis on k. So let's go ahead and build our Ruth array. So 1s to the cubed plus ks squared plus 20k times s plus 100k. So we'll do every other value. S cubed is going to be 1 and 20k. S squared is k and then 100k. And we do a little bit of algebra. We find out that k equals to 5. That gives us our j omega crossing. So that's the gain value that gives us the j omega crossing. If we want to know exactly where that happens on the imaginary axis, we have to plug in the value of k, come up with a characteristic equation, and then the roots of this equation are plus or minus j10. So remember that plus or minus j10 is important because we're going to use that later when we draw the Nyquist. Okay, so now we know where we cross j omega. We know where we're going to end up because we end up at the zeros. We start at the poles, and we know where the real axis points are. We also know that we're going to leave the real axis, cross j omega, and then come back and join the real axis. But we don't know whether we're going to be joining it at minus 10 or whether we're going to be joining it at minus 30. But we know that here at minus 5 is where one of the poles is when k is equal to 5. So now let's look at the angles of departure and arrival. And of course, to do this, we're going to go ahead and label our poles, and then we're going to check the angle constraints. So first, let's do one of the zeros. The angle of z1 plus the angle of z2, so those are our two zeros, minus pole 1 minus pole 2 minus pole 3 must be equal to plus or minus 180 degrees. So just if we zoom in here on where these two zeros are at minus 10, both of these zeros are at the same place, and we're going to pick some point epsilon, which is pretty close to one of these zeros. We don't know exactly what the angle of epsilon with respect to the zeros is going to be, but it turns out that this point epsilon is going to have the same angle for z1 that it does for z2. So, because this is the case, we can rewrite angle z1 plus angle z2 as 2 angle z1. At this point epsilon, which is really close to the zeros, the angle of the poles is going to be minus 180 for each pole, because the angular difference here, for each one of the poles is going to be minus 180. So we get 3 minus 180s. It must equal plus or minus 180. So because we're rounding it off to either 360 to 0 values, we know that these two minus 180s don't really matter because they'll sum to minus 360. We'll end up subtracting those out. So 2 angle z1 must equal 360 degrees here, which tells us that z1 is equal to 180. Or, if we choose to subtract to add minus 180, on the other side we're going to be adding positive 180 to minus 180, we would see that 2 times angle of z1 is equal to 0. So this actually gives us our answer, that the angles of arrival at this 0 are both 180 degrees and 0 degrees, because one pole is going to be coming from the left and approaching these zeros, the other pole is coming from the right and approaching these zeros. So that gives us our angles of arrival. That tells us that we're going to be entering the real axis with the breakaway point at minus 30, not at minus 10. If the breakaway point was at minus 10, we'd see that our angles were plus and minus 90 here. Okay, so that gives us our arrival point. We know that we're going to pass through k equals 5, right here. And so that gives us our root locus. Huzzah! And this, by the way, is about where k equals 7 is. So k equals 7 is clearly stable on this root locus. So, if we wanted to know what our margins are, This is actually not possible to do from Root Locus. So usually we've been getting our margins from Bode, but Bode doesn't give us reliable margins in this case. Root Locus tells us that it's stable, but we can't get any margins at all from Root Locus. So now we need some help from Obi-Wan Nyquist. So let's remind ourselves what we're doing with our Nyquist criterion. We're designing a contour in the S-plane, and that contour needs to either include or exclude poles that are on the j-omega axis. So I'm going to include them here. So I've included 3 poles and I've drawn the contour around them. So I'm going to pick a bunch of points, A, B, C, D, and E, and obtain the other points by symmetry. And I'm going to go around these points A, B, C, D, E, track from E back down to minus j infinity, and then draw their corresponding shape in the f of s plane. So let's go ahead and draw the f of s plane, or in this case the g of j omega plane. So we have both imaginary and real parts here. So again, I'm going to be taking all of those values of a, b, c, d, and e and evaluate them in g of s as g of j omega. So for example, our point A is equal to minus epsilon 0. So epsilon, of course, is a really small number, epsilon close to the origin. The imaginary value is 0, and the real value is minus epsilon. So we're going to use these to calculate the gain and the angle in the f of s plane. So c is going to be equal to 0 and then epsilon. B is going to be some value of epsilon angle minus 130, or epsilon angle 135, for example. And then D, I'll tell you later and remind you that we already calculated the j omega crossing point. D and E will also be evaluated. So let's go ahead and evaluate A. So what is G at minus epsilon? Well, 10 plus minus epsilon is basically 10. And so we're taking away a really small number from 10 and squaring it, so that's going to be about 100. And then we're dividing by the negative of a really small number. So the gain is infinity as epsilon approaches 0. The angle, because we have a negative value on the bottom, its angle is minus 180. So 0 minus minus 180 gives us 180 degrees. So point A is at infinity gain and 180 degrees angle. So let's just approximate A prime as about right here. So now let's do the same for B, C, D, and E. Actually, I'm going to go ahead and do C because it's going to motivate us to think about why B is an important value. So for C, G of j epsilon. So again, we're adding a really small imaginary number to 10 and squaring it. And then we're dividing by an imaginary number that's really small cubed. So it's again about 100 divided by minus j epsilon cubed. So the gain, again, 100 divided by a really small number. Let's say that that's infinity. The angle is 0 minus, and then again we have in the denominator an angle of minus 90. So we're going to subtract away minus 90 to give us a gain of 90. Sorry, an angle of 90. So infinity and 90 degrees is where the point C prime is going to be. So now you might think, oh, I can just go ahead and draw the Nyquist in this direction from A to C. But now we see why B is important. So does A prime actually go towards C prime like this, or does it go the other way? So we can check using the point B. So we're going to evaluate B at still a radius of epsilon, but here an angle of 135. So epsilon angle 135 plus 10 squared divided by epsilon angle 135 cubed. So again, we have a really small number plus 10 that's going to be about 100. And divided by a number that's really small will give us infinity for our gain. Let me make this correct here. So the gain is basically infinity. And likewise, we're going to look at the angle. So here we have 0 minus 3 times angle 135. So that's minus 405, which is minus 45 minus 360. So because we're going to normalize between 0 and 360, or minus 180 and 180, that gives us an angle of minus 45 degrees at a radius of infinity. So B prime is here. So we thought that A prime might go directly to C prime, but instead it goes through this point B prime in quadrant 4. So in order to make that happen, we go ahead and draw our Nyquist trace of the contour in this direction. So our radius is infinity, and our direction is from A prime to B prime to C prime. We'll make that clear in a moment. So now D prime. So the next part that we're interested in figuring out is where do we cross the real axis again. And we cross the real axis by finding out where our imaginary value is equal to 0. So I'm choosing D is equal to 0 and then J something. So actually, I remember from our previous root locus example that at J10 we had some interesting behaviors that were oscillatory. So I'm going to choose J10 here. So 10 angle 90 is J10 plus 10 squared divided by J10 cubed. So now we no longer get approximately 10 on the top. We have to actually multiply this out because the magnitude of the imaginary part is approximately equal to the magnitude of the real part. So after we do these bits out, we see that the real parts are going to cancel. In fact, the j's themselves are going to cancel. And so we're going to get minus 2 over 10, or minus 0.5. So here we have an only real part in the Nyquist, in the f of s plane. Our result is real, and the angle is minus 180. So this is the point D prime. So now we see that C prime goes directly to D prime, and then E at J infinity is going to tell us how we approach the origin. So J infinity over J infinity cubed gives us minus infinity squared over minus J infinity cubed. That's not exactly right. Or 1 over J infinity. So 1 over J infinity's magnitude, its gain, is about 0. And the angle is minus 90. So we're approaching sort of from the bottom here. Exactly like this. So now we're tracking in on the origin. And we use symmetry to get the other results. So now this is our direction, and we have another loop that we do here in this direction. Okay, so we evaluated A, B, C, D, and E, and we've used symmetry to get the other pieces. The point D prime is at minus 0.5. So now, let's recall that the number of loops that we're doing here, n equals minus 1, comes from our big outer loop. N equals minus 2 comes from this inner loop that we do. And n equals minus 3 comes from this innermost loop. And you'll remember that we included 3 poles. P was equal to 3 in our contour gamma of S that we drew. So we need n equal to minus 3. That is, we need to have 3 counterclockwise loops that we do around our critical point. So because that's the case, and we know that D prime again is at minus 0.5, sorry, minus 0.2, minus 1 over 5. So minus 1 over k must be greater than minus 1 over 5, or minus 0.2. And that's because if D prime is at minus 0.2, we need, if I can just sort of sketch here for a second, we need for 1 over k to be in between these two values. Because if we're not in between there, we're not going to have 3 loops around the point. And so the value of k is going to give us, if we choose k at the right value, it's going to put us inside the value minus 0.2 on the real axis. So minus 1 over k must be greater than minus 0.2 after we do a few negative sign multiplications and then move the k to the other side, move the 0.2 underneath the 1, we get that our stability condition is that k must be greater than 5. So we saw this, by the way, if we can look back on the root locus, we saw that k equals 5 tells us that we need a k value larger than 5 in order to be in the left-hand plane. The advantage with using the Nyquist is that now we can use the traditional Nyquist checks of where do we leave the circle of radius 1 and what's the angle at which we leave the circled radius 1 to calculate our gain margin and our phase margin. So Nyquist gives us much more information in these systems where a Bode is not useful, and where, if we need to know the margins, we can't get the answer from Root Locus.